This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Try to keep it simple.
Yes. Yes, this is not responding that either. So this is the IoT club, because I had to tell you that you are from the IoT club.
Yeah.
Okay. I think I had this issue previously. It's not in the display. Yeah, it's not I can get it connected.
Oh, I'm not sure, maybe connected.
Yeah, I think what happens is maybe we have to restart, unfortunately.
Okay.
Yeah, it happened with me previously.
Right.
So how many people are there in your club?
Sorry?
How many people are there in your club?
So we actually just started, but then we already got around 300 also members.
Okay.
In the past 3 weeks.
Oh, okay, that's great. So
Yeah.
what activities you are planning?
So we actually have workshops and social events. So today is for the social events, but we run workshops like Raspberry Pi applications and backend API development as well.
Good, that's good.
Yeah. So it's very related. So.
Yeah, I think now it will work. So that's the reason it was not allowing us to copy.
Okay. I see.
Yeah, now I think the screen will be, I think now it will be fine here. Yeah, you're stuffing. Paste it.
Oh, now it works.
Yeah. Then what I will do is, I will remove and then I plug in mine.
Yep.
Because after that, otherwise there will be any interruption. So that there is a continuity. I will be switching on the light again, switching off the light. Okay. Okay, you got it.
Do I have the mic?
Mic is here, you can use it. Yeah, maybe I'll introduce you. Good afternoon. So we have a gentleman who would like to talk to you regarding a IoT club. Maybe, for a minute or two.
Yeah. Thank you, everyone. So, okay, how's it going, everyone? And I'm from the Internet of Things Club. So maybe a show of hands, how many of you knows about Internet of Things technology? Okay, a few, that's good. A little bit worried, but that's okay. So that's what we're here for, Internet of Things Club. So we aim to raise awareness of the technology Internet of Things. And we aim to provide a platform where students can learn how to start their own Internet of Things-based projects through hardware and software. So we run both social events as well as workshops throughout the year. Every Tuesday, we'll have workshops. So this week is about the application of Raspberry Pi, but it's already been filled up. So next week, it's going to be a backend API development with Flask. So now I'm just going to introduce our next week's social events, which is called Amfest. So you may be wondering what it's all about. Well, I'm not going to spoil that. You're going to come to our events and you'll find out. So on the event, we'll be using something called Kahoot, and we'll be playing some games and trivia nights. And the question will be including technology related or general. And of course, we've got some modern internet memes questions. It's up to you. Then there will be going to be prizes to win, right? It's going to be pretty exciting. And most importantly, we will have free food. So we've got some ice cream, drinks, and pizzas. So it's okay if you just come here for dinner. We don't mind that. Just come. So if you want to follow up on the Facebook, there'll be events there, so you can just click join in so I know who's coming and can be prepared for the people coming. And yeah, so to join the club is very simple. Sign up on our Facebook page or come down to one of our events. So it's $2 per year membership fee. I know, right? It's a big bargain. And so make sure to follow us on Facebook, and more exciting events will coming up. So thank you so much. I hope to see you guys there.
Okay, thank you.
Thanks.
Maybe it's a good deal because $2 you can get a 1-year membership, less than a coffee. If they provide a coffee, you've benefited.
Yeah, free coffee. So okay, thank you.
Yeah, in the last lecture we discussed about voltage headroom. See, after my lecture, some of you asked about voltage headroom. Then I thought maybe I will show once again my drawing so that it is clear. So what is voltage headroom? So I drew it before coming to the lecture theatre. So voltage headroom is, so this space is called voltage headroom. Because you give a VB that is equal to 0.7 volt, that is for biasing here. So that is your VB, and then you connect a signal here. So you already got a biasing here, that is 0.7 volt. Then you are connecting a signal. So that is the signal. So your signal, when you measure the voltage here using an oscilloscope, what you see is you got a DC 0.7, then a signal riding on it. And then VC, you got 1 volt, maybe 1 volt depending upon this RL. Then what happens is your amplified signal will be riding on the top, inverted, and then this space, because the 1 volt and then this is 0 volt. So this space is called voltage headroom. So now it is clear, so there is no confusion. And then in order to increase the gain, what you can do is you will increase the RL. Then when you increase the RL, what will happen is your gain equal to minus GM into RC. So I'll put here RC. Then when you increase RC, you can increase the gain, but the problem is then your VC, that is equal to VCC minus IC into RC, and then this will increase, so VC will decrease, and then it will come to 0.8. But then you may get a higher gain, then what will happen is your voltage headroom will decrease. That's what happens. So as long as you got a very, very small signal, then it is fine. Even if you are decreasing the voltage headroom, as long as it is not touching the 0, that is fine. But if you are touching the 0, if you are connecting a very large input voltage, in the sense, not very large means not a very big value like 1 volt, maybe millivolt, because very small value is maybe a few microvolt. That may be the, here maybe if you connect a millivolt signal and if you got a very high amplification, and then if VC equal to 1 volt, what will happen is it will come down, but then there is no space, so you will get a clipping. Then again it will go up, and then again it will come down, and then you will get a clipping. So your waveform will be clipped. So that will have, that's why you get clipping. Then question for you, why it is not clipped in the upper side? Yeah, 3 volt. If I put here maybe 1.5 volt, just an example, then what will happen is here also it will clip it. Because you got VCC, very high voltage, so it can go up to VCC, close to VCC. You know what I meant? So if you connect 1.5 volt, what will happen is this is your 1 volt, and then it can't swing more than 1.5 volt. Then it will come down, you got clipping. Here also you got clipping. Here also you got clipping. So if you want to make a square waveform, maybe this is the best way. Using one transistor, you can make some square waveform. Okay, so now we will come back. So then we discussed all these concepts. Yeah, so then voltage gain with emitter degeneration, that's what we discussed in the last lecture. And we assumed that VA equal to infinity. There is no early effect. By inserting a resistor in series with the emitter, we degenerate the common emitter stage. So we degenerate the gain actually. Then we found out by deriving, so we got the small signal, then we derived the expression, and then we came up to here. So V out by V in, which is equal to GM RC by 1 plus 1 by R pi plus GM into RA. And then R pi, that is equal to beta by GM. Maybe you can substitute here. Then what will happen is you get GM RC by 1 plus GM into RE. So if you look at this equation, you can see without RE, when RE equal to 0, then this term has gone. So you got your equation AV equal to minus GM into RC. That is a gain without emitter resistor. But when you connect emitter resistor, what happens is your gain decreased by 1 plus GM into RE. See, you are decreasing the gain, but then you got other advantages. We already studied when you have emitter degeneration, we have advantages like this resistor will absorb any variation in the Vx here, any variation is there that will absorb here. This circuit is somewhat independent of beta. Then it is also more prone to resistor value tolerances, which we already proved. But then we are paying a cost, that is, we are reducing the gain by 1 plus GM into RE. But then this circuit, even we can make it independent of GM. What we can do is, we got voltage gain, that is equal to RC by 1 by GM plus RE. Means you can take GM from denominator and numerator and denominator, you can cancel out. So you get minus RC by 1 by GM plus RE. So if you take this condition, your RE is very large than 1 by GM. So if you take RE larger than 1 by GM, then you can write voltage gain equal to minus RC by RE. See, now your gain is independent of GM, none of the small signal parameters. So that is really good. So if you got only it's depending on your RC and RE, that will give you the gain, approximately RC by RE. That is very good. So that now your gain is independent of GM, independent of collector current, and if you choose resistances carefully, any variation that will cancel out. So your gain is kind of, you can fix it. And it's not depending upon the transistor. So then what is the advantage of this? If it is not depending upon transistor, so there is an advantage. Like I designed the amplifier, and then from the data sheet, I got beta equal to 100. That's what amplifier I used, a transistor amplifier. Then I made some mistake, my transistor got burned. Then I go to the market, get another transistor, and then replace my current transistor. Then what will happen is my beta is not 100, maybe 110, and then your circuit parameters might change. But if you got a gain independent of your GM, then no matter what transistor you are putting in, the transistor got burned, you got another transistor, go and market, buy another transistor, somewhat similar characteristics. Means if you are using NPN, you should buy NPN, okay? Not buy PNP. NPN somewhat closer to the characteristics, and you put it in because your gain is independent of the transistor, RC by RE. So that's the beauty of the circuit. So with emitter degeneration, we can do lots of things. Interesting things means I would say we have more advantages than disadvantage of reducing the gain a little bit, smaller. That is fine. 1 plus GM into RE, your gain is reducing, but we are getting lots of advantages. Like in negative feedback. We got negative feedback in the system. When you have negative feedback, you are increasing the stability at the cost of reducing the gain. Same thing happens here. So this RE is actually producing a negative feedback to the circuit. I will talk about that one in the next lecture. And then, so this voltage gain now is independent of small signal parameters if you got emitter degeneration. Then, now what we are going to do is we are going to look at the emitter degeneration as a block. So what I meant is, so this is your transistor, and then transistor is a voltage controlled current source. So this is V in, and then I out, and then this is your RE. You get the small signal. When I draw the small signal, you got R pi, then RE, then GM V pi, and then this is your I out. So your I out, I can write which is equal to GM into V pi, because this I out is providing GM into V pi. And then V in, I can write it V in, which is equal to V pi plus VRE, which is equal to V pi plus VRE. What is the voltage here? So there are two currents passing through RE. That is V pi by R pi. Here it is positive, here it is negative. So this is the direction of the current. Then GM V pi, because this is positive, this is negative, this is down. So both the currents are coming. From here the current is coming, here the current is coming, both are flowing through this one. So the voltage here is sum of the currents, GM V pi plus V pi by R pi into RE. So that's the reason we got this equation. Then we can rearrange and get expression for V pi. That's equal to V in by 1 plus 1 by R pi plus GM into RE. Because we need here I out is there, then we got something in terms of V in. Then when you substitute here, because we haven't taken into account early effective, because if you take into account early effective, you will have RO here. Then I out equal to, from this equation, so V pi, this V pi we substitute here, GM into V in by 1 plus 1 by R pi plus GM into RE. So then we can decide, so then we define a term called I out by V in, output current divided by input voltage. And then that is a small transconductance when you don't have RE. Because we got RE, this is I out, this is V in. So we define a capital GM, that is called a big transconductance, which is equal to GM by 1 plus GM into RE. So we can also represent like this. So the advantage of this is then we are representing this as a black box. So I'll draw it and show you. So which is equal to 1 by GM plus RE. If you take GM out and cancel out in the numerator and denominator. So if RC is the load resistor, the voltage gain I can write as minus GM into RC, capital GM, independent of transistor transconductance and hence bias current. So then this is called a black box representation. So black box representation is nothing. When I summarize it is clear. So I have shown the equations. So what it meant is, so when you have a transistor, simple transistor, so this is your VCC, this is your RC, this is your V in, then you grounded. So your gain equal to minus GM into RC. So this GM is a transconductance, that is equal to output current IC by your VB. So that is a transconductance. But then when you have a resistor here, so next case is when you have a resistor here, what I can do is, so you got now RE here. So you look at the RE and then you got RC, then VCC. So then this we can also write it as something like this term. So I will write a voltage gain equal to minus capital GM into RC. So then, so this is output. So this is output. This is output. So then this is called a black box representation. So it's kind of representing like this. So we represent this part like a black box. Then so we write this is a capital transconductance. Then we will write this capital GM, which is equal to GM by 1 plus GM into RE. So when you have RE, you can write it the same way, but then that we will be using a capital GM, that is equal to small GM by 1 plus GM into RE. So then it's a way of representation. So it is called a black box representation. Then the black box representation will make sense later when you have big circuit. Then we will be writing, when you have couple of transistors connected together, then we have to find out what is the total transconductance. So then we will be using this type analysis, black box representation, then we will be writing as a capital GM. So we will come to that point. Now we don't have any problem because you got only one transistor, the transconductance is GM. But when you have so many transistors, then we will be using a capital GM, like total transconductance, we will be finding out. Yeah, this is just an introduction for that one. We will be studying later about this type, derivation. But now what you have to understand is when you have RE, we can represent still like minus GM into RC, but then we will be using capital GM. Then capital GM equal to total output current divided by whatever you connect here, that is the input. So GM into RE is much greater than unity. So GM is more linear, the capital GM from here, because this GM RE is more greater than 1, so that it will become, if GM RE is much larger than 1, what will happen is this will become approximately equal to GM into RE, and then GM will cancel out, and then you get GM equal to 1 by RE, approximately equal to. That is the reason GM is more linear, because your resistor variation is more linear. So emitter degeneration example. So we have got this equation. Yep, sorry. So we have got this equation, that is voltage gain equal to RC by 1 by Gm plus Re with Re, emitter degeneration, when you have an emitter resistance. Then my question is, I am going to connect another transistor here. See, from here I am going to connect a transistor here. And then the input impedance is R pi 2. Then what is the voltage gain, the expression? So we don't have to always derive the equation. Maybe once you got one equation, you can find out what it will add, the extra circuit, what it will be contributing to the current equation. So what change is coming here? So if I connect here, so you got an R pi, and then the R pi 2 is coming in parallel with Re. So that is the only thing the other transistor is doing. Because from here you are taking, you have connected here, and then you can draw the small signal, then the R pi is coming, R pi 2 is coming in parallel with Re. Then you can write down, see, R pi 2, because that is the only thing it is affecting. So the equation becomes voltage gain equal to minus RC by 1 by Gm1, because here I have written, because here you got two transistors, so the transconductance of the first transistor, because this equation is for this transistor, and then Gm1 plus Re parallel R pi 2, because this R pi 2 is coming from the second transistor. So that's coming in parallel, that's all. Means when you draw the small signal, you don't have to draw the full small signal actually for this one. So you already got the transistor, and then we got the transistor. So this is your VCC, and then what we did is here you got Re. Then from here, oh sorry, yeah, from here what is happening is you are going to connect one more transistor. So when you connect one more transistor, so that is other transistor is grounded if you check it, and then this is your VCC. Then so this is the point it is connecting here. So if you draw small signal, you are getting R pi 2, that is ground. Then you are getting the voltage controlled current source, and then this is ground, because this VCC equal to ground. And then so this is coming in parallel with this R pi 2. So that is the reason we have written here in the voltage expression. If you want, you can derive it. You can draw the small signal, maybe a good exercise for you. Draw the small signal for this one, emitter degeneration. We already found out the gain, and then you got another transistor you connected together. Then you check whether you can get this equation. Maybe it's a good exercise to check your knowledge on small signal. It is simple because we already derived this expression. And then the only thing is you are connecting one more transistor, but then you will get something similar. Re parallel R pi 2. So the input impedance of Q2 can be combined in parallel with Re to yield an equivalent impedance that degenerates Q1. Means it is coming in parallel with Re. How about this one? So the previous one is we have connected a Re, and then from Re we connected to the base of Q2. Then we got R pi 2. So now what is happening is we connected to the collector. So what is the equation? So think of the small signal. So by looking at this circuit, you can see the small signal, what will happen? The VCC will be grounded, isn't it? Because that is a constant DC voltage. This will be anyway grounded. And then that is coming in parallel with your R pi. So then your equation will become R pi 2. You are getting R pi 2 here. So then it will become RC parallel R pi 2 by 1 by Gm1 plus Re. So what I am trying to teach you is you don't need the small signal to understand the gain. Once you know the gain of some circuit, you can find out when you connect what happens. Maybe you should be, you should be now that level. Like, you can understand. See here, in this circuit, when you draw the small signal, it is pretty straightforward. If you are confused, you can draw the small signal. See. So you got one transistor, so I am going to draw the small signal directly. So you got one R pi, then you have got Re, and then this is your R pi 1, and then this is your V in. Then you got a voltage controlled current source, and then you got RC. RC will be grounding because anyway that is a constant DC voltage. Then what is happening is you are connecting this RC, this point, this is the output point, to the base of another transistor. So from here it is coming, then you are getting a, see, something like this, and then this part is grounded. So that's all. And then what is happening is this R pi 2. So this R pi 2. So this is GM1, V pi 1. So GM2, V pi 2. See, these both are coming in parallel because this VCC here, that is a DC, so we ground it. So RC parallel R pi 2. So if you are confused, you can draw the small signal, but then even without drawing, you should be able to see how it is affecting. See, here then you can immediately visualize this is equal to ground. This is the ground part. And then this is coming in parallel with R pi 2. So RC parallel R pi 2. Then input and output impedance of degenerated common emitter stage. Because that is an important aspect. When you have degeneration, now we are going to find out what is the input and output impedance. Because with the degeneration, we found out lots of advantages, though gain is reduced a little bit. But now, when you use degeneration for when you use degeneration for designing the circuits, we should know what is the input impedance and output impedance, because you should have maximum input impedance and very low output impedance. So we are going to check with degeneration. Maybe before that, I will check if you are sleeping or not. So when you have this transistor, so there is no degeneration. So VCC, and then this is RC, this is your output, and then this is your V input. So there is no degeneration here. So what is the input impedance? Infinity. How many of you? Okay, good that you are not sleeping. Otherwise you may say, oh, yes, wake up and say, yeah, infinity. So what is the input impedance? Yeah, R pi, you can just draw the small signal. So if you draw the small signal, you can see that is your input impedance is R pi, nothing else. How about R? So now I take VA equal to infinity. How about output impedance? Yep. So output impedance equal to RC, and then so because RC is coming in parallel with maybe the infinity, RO equal to infinity. So infinity parallel, the small one predominates, so RC. That is good. So this is a case when you don't have any emitter degeneration. So what now we are studying is when you connect this RE, what will happen to the input impedance and output impedance. Then when you connect RE, what is happening is you are connecting RE here with emitter degeneration. Then now what is the input impedance? Yeah, so that is so we already from this we will see that it's R pi plus RE, but then why? Because it looks like R pi RE, but transistor is an active circuit. Your impedance is again depending upon the other values, because here, from here the current is coming and flowing, same way the current is flowing through this one. So that is not R pi plus RE. It is much bigger than that. So that's what we are going to show that. So because the transistor is an active device, if you got only one resistor here, R1, you connect another one here, that is R2, then that is fine. You can say that when you look from here, R1 plus R2. But because this is an active device, current is flowing here, current is flowing here, so it is different. That is what we are going to show. So then, in order to find out input and output, so first we are going to find out input impedance. So whenever you want to find out input impedance, the rule is connect a test voltage source. So please remember the rules. Connect a test voltage source at the input, and then we don't need to short the output. You connect a test voltage source, that is Vx, and then Ix current is going in. And then when the Ix current is going in, so V pi, because Ix current is flowing through R pi, so your R pi into Ix, that is your V pi here, because Ix current is going in. Now we are going to write down the equation. How about the input impedance? We already said that is not R pi plus Re, because it's an active device, and then you got the currents. We have to pay attention to the currents. So current through RE, the current through RE is, you got IX coming. IX is coming from this direction to this point and passing through RE. You also got GM into V pi, that is coming and then going through RE. So IX plus GM into V pi, that is the total current through RE, which is equal to IX plus, then what is V pi? So V pi equal to Ix into R pi, because Ix is the current passing through R pi. So that is equal to Gm R pi into Ix, which is equal to 1 plus beta into Ix. So that is the current through Re. Then we already said the Va equal to infinity, no early effect, so that your Ro equal to infinity. Then Vx, when you write Vx using KVL, Vx equal to Ix into R pi plus this voltage, whatever the voltage you see here, that is a voltage across Re, and then which is equal to plus, what is the voltage across Re? Because current through Re equal to 1 plus beta into Ix, that is a current through Re. So voltage across Re is this current into Re. So Re into 1 plus beta into Ix. So then we are going to find out input impedance. So Ix is here, you take it out, common Ix, then Vx by Ix, that is your input impedance. That's what we do with the test voltage source. We connect a test voltage source and then we find out Vx by Ix, and then we assume that Ix current is going in. So then we get an expression so that we get Vx by Ix, which is equal to R pi plus C plus beta plus 1 into Re. So it's not just R pi plus Re. So we are getting beta plus 1 times Re. So that's a big value. So with emitter degeneration, what we are getting is a boost in the input impedance, which is good. Because that's what we need. A voltage amplifier ideally should have infinite impedance or very high input impedance, because we want there is no loading. Your signal is not attenuated. So this is not just R pi plus Re, because this is an active device. We have to take into account the currents for the transistor. So when we derive, see Rn equal to R pi plus beta plus times Re. So your input impedance is boosted. That is very good with emitter degeneration. Then how about output impedance? So in order to find out output impedance, again the rule, connect a test voltage source Vx and assume that Ix current is going in. Yes, we did it. Then for output impedance, one more thing, you have to short the input. But then when you find out input impedance, you don't have to short the output, which I already said, because it is not affecting, anything happens in the output is not affecting the input, because there is an isolation. If something fluctuates here, nothing will happen to the input, because your input is isolated from the output. But when you measure the output impedance, we short the input, because if something varies in the input, it will be affected in the output, maybe multiplied by several times. And then in order to avoid that, we short the input. So whenever you find out input impedance, you connect a test voltage source, Ix current is going in, then you can leave the output open. So whenever you find out output impedance, please remember, you connect a test voltage source at the output, but then you short the input. And then here, so what is output impedance? Even without writing down the equation, we can say what is output impedance. So what is the output impedance? So maybe I will ask, what is GM pi here? Why GM pi is 0? Yeah, because here input you have grounded. Here there is a ground, then here it's a ground. So when this point is ground, no current can flow between these two. You know what I meant? Then this is 0. So this voltage equal to 0. So then V pi equal to 0. So this Ix will flow through this RC. Then we get Vx by Ix, which is equal to RC. So I have written Va equal to infinity, so V in equal to 0, because you can write down V pi plus V pi by R pi, that is the total current, plus Gm into V pi, this current into Re, which is equal to 0. So R out equal to Vx by Ix, which is equal to RC. You don't have to write down anything. From by looking at, you can see this is ground, no current will flow between these 2 points, so it is 0. And then, so this is 0, so you got Vx by Ix, which is equal to RC. Emitter degeneration increases input impedance. Output impedance is not affected. And so emitter degeneration is good. Emitter degeneration does not alter the output impedance. Now what we are going to do is, whenever you design an amplifier, we are using the emitter degeneration, because emitter degeneration got lots of advantages. But then when you connect a microphone, then what happens is when you connect to the input of the amplifier, this microphone got an output impedance. So this microphone, maybe if I am connecting to an amplifier input to the base, what is happening is this one got an output impedance, but that will come in series with your base. So in the amplifier, then we have to take into account a series resistance. So the series resistance is, we call it as RB. So when in the amplifier configuration, we take this RB, then we find out what is the gain with RB. Why we take into account this RB is, this is kind of the impedance of source that you connect to the amplifier input. Maybe for example microphone, when you connect microphone to the base, then the RB is the output impedance of your microphone. Or if it may be something else, some sensor you are connecting to the input which is giving you some voltage, then that is output impedance of that sensor. So we write down the equation with this RB, because otherwise what will happen is you connect your microphone, then your gain may be different. Then you should know how much different it is. So then you read the data sheet, oh, this is the output impedance of the microphone. Then you know that, okay, in the gain expression, then we have to modify this change. Then only we have to take into account this RB. So then when we have RB here, what will happen is your equation, this could be a microphone resistance or output impedance of the previous stage. If you are designing multi-stages, it may be the output impedance of the preceding stage. Then with series resistance, the voltage gain will become minus RC. So here it is minus RC. Then you get 1 by GM is same as this one, plus RE. Then you get a term plus RB by beta plus 1. See, so your RB divided by beta plus 1 is your voltage gain. So you don't have to study the derivation. Obviously, if you are interested, you can derive the expression. But then we are not focusing on the derivation part. We are understanding the concepts, because our interest is designing the real circuits. And then, so with series resistance, what will happen is minus RC by 1 by GM plus RE plus RB by beta plus 1. Having said that, this is again is a good exercise for mastering the small signal. Just maybe you draw the small signal and understand how can you get this RB by beta plus 1. So if you don't get it, you can email me or you can come and see me during my consultation. Maybe this is a good exercise here, though it is not important from the circuit design point of view or examination point of view, but it's a very good exercise to master the small signal, because it is not that straightforward to get this expression, because here there is an approximately equal to, because you get a bit complex equation, you have to approximate it. So then you get a RB by beta plus 1. Then input impedance. So input impedance is again, when you look at it, previously we got R pi plus beta plus 1 into RE. So that is your input impedance when you look from here. R pi plus beta plus 1 into RE. But then when you connect RB here, this RB is just coming in series, because that is not affected by any of the currents. So we can write RB plus R pi plus beta plus 1 into RE. So input impedance, there is no complication. Output impedance same. Only the voltage gain is affected. That we get RB by beta plus 1. When RB equal to 0, means you don't have any input impedance, something like here. So that you get this expression, RC by 1 by GM plus RE. Yeah, so this is then what we understand is, see, here what is happening is, you connected something RB here, and then this is output. So from the output point of view, RB reduced by beta plus 1. See, RB by beta plus 1. So the RB divided by beta plus 1 is the effect on the gain equation. When you look from here, see, you know what I meant? It's not just RB. RB by beta plus 1 means the effect on the gain is very, very small. This RB. RB is producing very, very small. Same way, when you look from here, when you look from the input side, the R is multiplied by beta plus 1. See, that is the reason here it is showing. So when you look from the input, what you see is, this is just an observation. When you look from input side, your R is multiplied by beta plus 1. But then when you look from the output to the input, then you got a RB here. That RB is divided by beta plus 1. Or you can think of other way around. So in the transistor, here you get an amplification, maybe beta. So beta plus 1 into RE. Then when you look from here, whatever you see is RB by beta plus 1. You know, that's just an observation. When you look from here, from the input side, what is happening is your input impedance actually boosted by beta plus 1 into Re. So when you look from here, this Re, the effect on the Re is beta plus 1 times. But when you look from here output, V out, when you look into here, what you see is Rb by beta plus 1. That's what I have shown. So with series resistance, without series resistance, we got these equations, and then with so then another thing is, so this is the equation. Now we are studying the different topologies. So without series resistance, AV equal to minus RC by 1 by GM plus RE. Now we are going to provide the bias. So when we provide the bias, if you look at the equation, your voltage gain equal to minus RC by 1 by GM plus RE, your input impedance, R pi plus beta plus 1 into Re, that is here. That is coming in parallel with R1 parallel R2. That we can understand. R out equal to RC. So my question is, why this R1 and R2 is not affecting the voltage gain? Is it a mistake, or why it is not affecting? Because when you draw the small signal, it will be clear. So that R1 and R2 is only affecting the input impedance. Because you got the circuit, so this is your circuit. So this is your R1, this is your R2, and then this is your RC, and then this is your transistor. So this is your base, and then this is your Re. This is output. So when you draw the small signal, so this is your input, and then this is your VCC. So when you draw the small signal, what you will see is, so I am going to draw from this point. So this point, I come here. Then what will happen? So R2 grounded. Then what will happen to the R1? Grounded. Then you are getting R pi. Then your Re. R pi. So this is your V in. And then you are getting the voltage controlled current source. Then you are getting your RC to ground, and then this is your output. So V out. So look at this equation. So when you look at this equation, so what is the difference here? So R1, R2, R pi. So this is equal to GM into V pi. See GM, this is the V pi. So this R1 and R2 are coming in parallel. Means if you don't have this R1 and R2, then you measure the voltage. Your V in equal to maybe X volt. So that the X volt will come here. So R1, R2, how can I get rid of R1, R2? If I put R1, R2 infinity, very big, then you can look at here, R1, R2 infinity means then you don't have that R1 and R2 open. That is same as the left case. Then R1, R2 equal to infinity means you don't have these two. Then what is the voltage? If you connect X volt here, you get how much volt? X volt here. But then when you connect R1 and R2, because this is coming in parallel with this one, nothing is happening here. Even you connect another resistor, then the input impedance is different, but you get the same voltage. You know what I meant? Means you connect a 5 volt here, you connect a 5 volt, then you got one resistor here, then you get 5 volt. You connect another resistor here, still you get 5 volt. You know what I meant? You get another resistor here, still you measure 5 volt here. But the problem will start when you have a potential divider. But if you connect everything in parallel, you get still 5 volt. That is the reason here there is no effect in the voltage gain, but then it is affecting the input impedance. Input impedance will become R1, R2 in parallel with whatever you get here, R pi. So that's the reason here you are getting a R pi plus beta plus 1 Re parallel R1 parallel R2 with resistive divider. Then now I have connected a capacitor. So if I connect a capacitor, what will happen? In the small signal, what will happen to capacitor? Yeah, capacitor is a short. Then what will happen? Your R is short. So in the small signal, again I will go back to my previous drawing. It is easy to show in the same drawing. So you got here. So now what is happening is you got Re. See here, if you are connecting a capacitor, means in the small signal that is equal to a short. Then you don't have the effect of Re. Then what will happen to the equation? So what change will happen to the equation? So what will happen to this equation? When you don't have Re, then what will happen? So you get AV equal to minus GM into RC. See, for the signal, you got rid of the Re effect. So in this circuit, what will happen is your DC current, still your collector current, when you don't have any signal here, then you got the collector current. That is a biased DC current that will be flowing and coming here to this point. Then this DC current, what will happen? Will it go through the capacitor or resistor or dividing here? So there are three questions. So DC current is coming here. First answer number one, it will branch out into RE, branch out through RE and C1. How many of you think? Branch out, then it will flow only through C1. How many? Okay, it will flow only through RE. Nobody. So the DC current will not flow through the capacitor because your DC current means the frequency equal to 0. So the capacitive impedance equal to 1 by 2 pi Fc. Then for the DC current, what will happen is your frequency equal to 0, then impedance is very high. So the DC current will flow through this one, RE, so that you got the bias. But then when you connect a signal, what will happen is the signal current, the current due to the signal, that will come up to this point, and then because this got least impedance, so your signal current will be flowing through the capacitor to the ground. So that this capacitor you should be choosing carefully. If this capacitive impedance, that is equal to 1 by 2 pi Fc, if this impedance equal to this Re, what will happen is your signal current will split into two. But if this capacitance is a bigger value, impedance equal to bigger value, your signal current and this DC current will flow through this Re, you don't have any effect. But this impedance is very, very small, so you can choose a big capacitor value. Then because your capacity impedance equal to 1 by 2 pi Fc, so that is your capacity impedance. So the capacity impedance equal to 1 by 2 pi Fc, so this equation, and the F equal to 0 means that is a DC. When you have DC, capacitor will block it, infinite impedance. But then if you choose a very big capacitor, what will happen is your impedance is very, very small. So then when your impedance is very, very small, for the signal, what happens is the signal will go through the least impedance path. So signal current will come, this one got least impedance, so that it will come through the capacitor to the ground. So that is the reason the small signal, we don't have the effect of Re because we are shorting. That's the reason here we got AV equal to minus GM into RC, Rin, which is equal to R pi parallel R1 parallel R2. Because you don't have the effect of Re now, because R equal to 0. And then R out, not changed. So coffee question. So we asked this question, and thanks to all who responded to my coffee question. The question was whether we can use this circuit diagram for amplification. And then in the modern BJTs have base widths around 100 nanometer. Why do we need a very thin base for transistors? If base width increases, what will happen to collector current? So why do we need a very thin base for the transistor? Why? Because here, see the circuit diagram. If you don't have very thin base, the N plus, here it is heavily doped. The electrons will come to the P junction, P region here, that is a base. And then if your base is very thin, you have only less recombination. So maybe 1000 is coming, 1000 electrons are coming here, you are losing maybe only 10, and 990 will come here as a collector current. If your base width is very thick, what will happen is 1000 will come, maybe you will lose 200 in the recombination if your thickness of the base is more, and you get only 800. So that is the reason we need a very thin base for transistor. That is the reason the modern transistors we have got 100 nanometer thick. Then the circuit below shows two diodes, two PN junctions connected together to get NPN. Can this circuit amplify a signal? You can't amplify. Why? Because you can see the spacing. Even if you make this is heavily doped, still because of this base, this width, this separation, no charge carriers will seep through this separation because of you connected with a wire. No matter you bring it together, still it is a big gap. Because here it is 100 nanometer, then you get a very good transistor. And then what is a current? Because here it is reverse biased, so it is a reverse saturation current. That's all. So answers are correct. I think I got so many replies. I thank you. I really enjoyed reading your answers. And then these 5 guys came top. Chen, Tao, Langsi, Yogesh, Shen, and Hevish. So I selected actually 6. Anyone here? Okay, you are here too. Okay, only 2 are here. So others, you get other again opportunities, sir. This is only coffee question 1. We got coffee question 2. So that you have to reply quickly and your answers also should be correct. So I got several correct answers and then I picked up 6. because there were so many. And some were very close in the timing, so you have to send it quickly. Maybe you may lose the coffee for 1 minute. And then remember that you should answer properly. So these guys, the lucky ones will get an invitation from me for coffee. So I'll buy your coffee of choice. Then I will continue in the next lecture. I think I'll come out and talk to you. We'll come out and because the other lecturer can come in. I think